So let's talk about actual conductors. So we know a little bit. So now this slide right here will start making a little bit of sense. And this is chapter 1. This should actually be lecture 2. I'll go back and change the PowerPoint. What is a conductor? What is an insulator? What is a semiconductor? How does current flow through conductors, insulators, and semiconductors? What are the key thermal, electrical, and physical characteristics of electrical insulators? How does light travel through the material? So we'll get a basic introduction in this section on fibers. We're not going to get into a lot of detail. So the first 8 weeks we're going to focus mainly on copper conductors, metal conductors. The first 4 weeks, and the second 4 weeks we're going to be primarily fiber optic. So, but here what we do, this first lecture, after we get through our basic electricity lecture, basically deals a little bit with both of them. And we've already talked about this, two-way power or information can be transmitted. We can do it wirelessly, which is really becoming very, very popular as wireless transmission of especially signals. It's still pretty hard to wirelessly transmit power, even though we kind of do it. So I've got a toothbrush, an electric toothbrush that I just put on a little charger. So it's wireless. It actually does that. It does it through induction. But still, we don't have the ability to transfer a lot of power. Wirelessly, we can use radio or we can use infrared. Conductors, we use metal or optical. Right? Are we okay there? Infrared, you run it out all the time. All your remotes on your TVs and all this other kind of stuff, that's infrared. And of course, radio. So Wi-Fi is radio. Your cell phones are radio. Right? You understand that. If you've got a high definition antenna, if you don't use cable, well, that's radio. So radio is information through the air, right? Terms. So voltage, we already know what voltage is. Electrical difference in potential that causes electrons to move. Static electricity, we're familiar with that. Lightning, we're familiar with that. Batteries, we're familiar with that. Generators, we're familiar with that. We're familiar with a lot of things that does that. Current, what's the current? Yeah, so we can't have current. Can't have current unless we have voltage. And you can't have work without having current. Resistance or reactance, anything that opposes the flow of electric current. And we also have what we call impedance. Impedance is technically a combination of these two. But like I said, in AC, you'll hear a lot of people talk about impedance when there's no reactance in the circuit at all. It's just a neat sounding term. Categories, conductors. Offers very little opposition to electrical current flow. Many free electrons. Most of our metals make good conductors. The two most widely used are what? Aluminum and copper. Gold, we use that for plating. Silver, we use that for plating. Insulators, they offer an extremely high resistance. We can't say it's infinite resistance because there is a path for current to get through, right? You understand? If you got a path for current to get through, and you put a difference in potential, there will be current flow. There is current flow through the insulator. Very few electrons. These are our rubbers, our plastics, fiberglass, ceramic. But the resistance is going to be in what? Millions of ohms, even gigohms, but it's still going to have a resistance. Most of our meters can't measure gigohms. They can measure up to so many megohms. But we do have a special meter I'll bring it called a megometer. And that meter's set up to measure in what? Megohms. So we'll bring this out and we'll actually measure the resistance of the insulator. We'll take one and we'll clamp it onto the conductor. We'll take the other lead and clamp it onto the insulator. And we'll crank that puppy up. And it puts out a real high voltage. I think ours puts out like 600 volts. So don't put your fingers across it, even though it's don't have any current available. And of course, then we have semiconductors. We need to understand semiconductors just a little bit because when we get into extremely high voltage conductors, they use layers of semiconductors to equalize the stress. But semiconductors are right in the center of what we call conductors and insulators. Now, what defines an element as being either a conductor or a semiconductor depends on the outermost shell, which we call the valence shell. So when I look at an atom, the shells move. So the maximum in the first shell could be 2, and then it keeps moving up, and they change. It's real weird. I had to learn that when I took chemistry, but I don't need to know it now. What we need to know is that outside shell has got to have at least 1 electron in it, and the maximum that it can ever have is 8. And this is the shell, where the conduction actually don't exist, but it's from that where the electrons come from. So the electrons that move into what we call the conduction band comes from the valence shell. Now, the ultimate goal is these things do what they can do, and they start bonding with each other, and they start sharing atoms. We call it covalent bonding, where they try to get 8 out there, because 8 is what we call a balanced electron. Once it's got 8 out there, it don't want to get rid of it. So what we're talking about, anything that has 3 or less, these make pretty good conductors. Of course, the best conductors would be the ones that's got what out there? 1. Aluminum, I think, has 3. So aluminum's not an extremely good conductor, but it's good enough if we can get the voltage up high enough, right? To compensate for the loss in the wire. And of course, so if we look at copper, it's got 1. If we look at gold, gold might have 2. I'd have to look at it. Silver has 1. Copper has 1. Insulators, elements with 5 to 8, make good insulators. Of course, the base would be one that's got 8 out there. 8. You don't want to bond with any. So 8, if it's got 8 electrons out there, it don't bond covalently. It bonds some other way. Chemically, we have chemical bonding, covalent bonding, and there's another one. Hydrogen bonding, hydrogen bonding. And then we have semiconductors. Semiconductors are elements that have 4 electrons in the valence shell. Natural semiconductors include carbon, silicon, germanium, tin, lead. What are volume? The 2 semiconductors that we use most often are silicon and germanium. Which, by the way, is gallium is starting to make a really big impact, because gallium is what we use in light-emitting diodes. They're gallium. Now, what we do is we introduce impurities into that. They call them impurities, but it's actually atoms. We use one we call trivalent, one we use polyvalent, which we don't even understand in this class. But what it does is when we add these other atoms in there, it changes the conduction characteristics of the semiconductor and allows us to control the flow electronically, which is pretty neat. So a semiconductor can be a variable resistor, but we don't control it mechanically, we control it electronically. These are your transistors. So your transistors is nothing but a variable resistor that you're controlling electronically, which is pretty neat. But with semiconductors, we can do all this. We can control the current flow with a very small applied current. We can control current flow with an applied voltage, these are FET. We can control the direction of control. We have diodes. These are our check valves of electrical current. They only let the current flow in one direction. These are the main devices that convert AC into DC. We have light-emitting diodes, which produce what? Light. We have photodiodes, which receive light. We have photovoltaic cells, which create voltage. These are your solar cells. These are semiconductors that absorb energy and create a different potential. We can use them to sense temperature. We can use them to get a gain. We can use them in all kind of stuff. So just that doping of those semiconductors gives us the ability to electronically control these devices, which is pretty neat. So when we say semiconductors, Usually we're actually talking about doped semiconductors. But in these cables that use semiconductors, these are semiconductors and are semiconductor layers. We can actually see them. Light principle. This is pretty interesting. So what is light? It's electromagnetic wave moving through air. And when it strikes these sensors in our eyes, then your light converts that over to vision. I mean, those electrical impulses makes our brain see things, which is, to me, totally amazing. And we evolved, right, from monkeys. AC flowing through a conductor in this electromagnetic wave. And we know that, and that gives us problems because those electromagnetic waves we can create. If we put loops of wire, we end up with inductance. If we put two wires together, those electromagnetic waves create electricity. Create capacitors. If we bring two conductors real close, we can actually induce voltages into the other. That's the way transformers work. So, material will either pass light easily, called what? Something that passes light easily, we use the term transparent. If it's hard to get through, it still gets through there, but it's hard, we call those translucent. And if it don't pass it at all, we call it opaque. Y'all have heard those terms before, right? Huh? Opaque. Refraction. This is another fiber term. The bending of light as it passes through materials that conduct light as it's reflected. Where do we run into this at? You may got an aquarium, fish. Ain't that weird? You look at them in front, they're here. You look them up there, they're in a different spot. Right? Because you're looking at refraction. So water, we have air and water. So anytime we have air and water and we look at it at a certain angle, we can see that refraction. I don't know if anybody's ever bow fished before. That's real hard to do because the fish is not where you're at. So the fish is usually either further away. I used to bow fish too. I got my cord hung around my arm with it. Yeah, frog, and if they're underwater, you have a problem. You don't, if you shoot for where you think they're at, you're going to miss them. But over time, you get that out. Refraction, attenuation. What's attenuation? Usually it means loss of signal over distance. And modulation, what we need to do is we need to have the ability, and this is in your terms too. We need to have the ability to do what we call multiplex. About multiplexing, anybody know what multiplexing is? What's multiplexing? Multiplexing is, so we have media. What's media? It's what information flows through. So what media am I using right now? Air. So that's my media. But you have the ability to talk. You have the ability to talk. And it gets very confusing. So multiplexing is a technique where we let multiple signals share the same media at the same time. So how many different signals do we have sharing this media right now? Bunch. Yeah, my cell phone, right? Anything cordless, Wi-Fi, wireless networking, sharing the media. All your broadcast radio stations are sharing the media right now, right? So if we multiplex, eventually we're going to have to separate the signals. The part of separating the signals is called demultiplexing. So if I want to multiplex, I got to have a demultiplexer somewhere, right? So that means we've got all those radio waves out there. Wait. Hurry. So they shake it like a tree. I don't know how long it's been paused. Oh, it paused. Fiber optic cables can carry what?
Very little.
No, yeah, we don't carry very little. Just enough of to trigger an LED, a photodiode. Can be used to transfer information because of higher frequency transfer a lot. Enormous amount of information. One of the big advantages of fiber optics is it's not affected by capacitance, it's not affected by inductance, there's no such thing as impedance, electromagnetic interference. Yeah, I mean, it don't use magnetic waves, and all this stuff generates electromagnetic waves. So we use copper inside here because it's a lot cheaper, but running the network from building A over here is fiber. So they don't have to worry about lightning striking or anything like that around the fiber because it won't hurt you. When we first started networking, these guys didn't know any different, and we had a firewall over in building A, and they couldn't get through the firewall. So what did they do? They ran it across the road, ran it through one of the vents, ran out of vent through the other room, and they blew out all the network cards in one whole room. Because what happened? Lightning struck close to it and blew the cards out. And man, I said, man, you can't run copper. You can't run signal wires outside like that unless you protect them. Electrical conductors can carry what? They can carry power, they can carry information, they can carry both. Like that. Of course, the wired telephone system is a perfect example. Far less expensive than fiber optic systems, subject to capacitance, inductance, and electromagnetic. Are we okay there? And these are all the things we're going to talk about. Attenuation, cladding, conductors, core, corona. Some of you ain't heard before. Critical angle, dielectric, equivalent circuit, insulator. You already know what that means. What is corona? Huh? Corona is a glow that things picked up caused by electrical potential. In the airplanes, they always used to call it somebody's fire. What did they call that? Every once in a while you'd be flying, because planes pick up a lot of static electricity because they're a pretty good conductor and you're moving them through electromagnetic waves. So it picks up a pretty good deal of static electricity. And they call it, what's it called? Something's fire. Where there'd be a blue flame that actually fall that would move through the plane. People thought it was cool. I never actually saw that. Some people said they did. But at night when you was flying, a lot of times you could look out on it had static whips on the very tip of you can't hardly see them anymore. They're just basically little metal things that, those little peg things that looks like they're on the back of the wing, those are out there. They help discharge the static as the plane builds up. The P3s use what we call static whips. They were actually a little thing that flipped in the wing. They were on the trailing edge of the wings. And at night, when it was flying at night, you could look out there and those things would be glowing a little bit. They were pretty neat. So our planes had big old copper bars. They were flexible. And when the plane landed, these were between the main gears. And when they landed, those things would actually hit the ground first to discharge the plane before the rubber tires hit them. And then when they parked the planes, they had to hook up a grounding rod to the plane to earth ground to keep the plane from building up its charge that way. So how do we get off on it? So corona is a glow caused by electromagnetic waves. Huh? Corona. Dielectric strength, equivalent fraction index. If you guys remember, look at, we're going to talk about cracking, freezing, something called volumetric current. And that's all inside this unit. So Ohm's law, so semiconductors. So when we talk about a conductor, we visualize it as having no resistance at all. But now we understand that there is no such thing as no resistance. And what determines the resistance of a conductor? Let's start off with number one. Yeah, material. Yeah, let's do the size next, and then the length, and then Tim. I can put them in this order right here. Metals, when you heat metals, their resistance goes up. When you cool metals down, their resistance goes down. That's why superconductors operate at extremely cold temperatures. And they're a graphite, by the way. They're not actually metals. But they operate those things in liquid nitrogen. They're cooled with liquid nitrogen. And that's why they get the resistance down so much. So they get the resistance almost down to zero. But we can't get to zero, but it's almost to zero. But it's very, very low, which is pretty neat. So now we can send 1,000,000 amps through a little old tiny wire that's almost nothing, right? Because it has no opposition. So the real, the equivalent circuit would be a resistor. Of course, anytime we put current through resistance, we get what we call a voltage drop. Anytime we get a voltage drop, we create power. Anytime we push current through a voltage drop, we get power. Power generates heat, which causes the resistance of the metal to go up. So unfortunately, we can't do much about that, guys. Like I said, either operate it at the same temperature all the time, which would be very, very hard, and then the resistance of the temperature would be the same if we operated at the same temperature. So everybody okay there? Now the other thing we have is we have insulator current. So this is the equivalent circuit of a conductor. So we have an insulator, then we have a plate, then we have the outside of the cable, which is the other plate. So basically the equivalent circuit is this. So there is a capacitance set up with a cable. So this is why a lot of cables or conductors are rated at certain frequencies. If you operate above that frequency, it's going to start giving you problems, right? So even your communication cables are going to be rated at a certain frequency that they can handle. Are we okay? So this shows you what happens. What happens is the current flow in the what the capacitor of the capacitance insulator starts causing to happen. It causes a phase shift between the current in here and the current out in the insulator. And of course it lags by 90 degrees, but that's no big deal. All we need to understand is that current, there is current flow in the insulator. A capacitor is created when two conductors are separated by an insulator. Virtually all electric circuits exhibit some capacitance. Capacitive current leads the resistance current by 90 degrees. X of C is determined by what? The material, the length, the thickness, and then also how clean you keep those insulators. So surface contaminant on the outside of the insulator has a lot to do with the capacitance of the length. Approximately 100 times greater than so the current flow in the circuit is about 100 times greater than the current flow in the insulator. I guess that's what that statement's trying to mean. The R of the insulator is determined by the material and its thickness. Volumetric current. So there's the current. What's that? Yeah, so that's the name of the current that flows through the insulator. Then we have what we call surface current. What's surface current? And what's it determined by? Contamination. So anytime we get any dirt or anything on the insulator, it's going to cause problems, right? The IR of the insulator is called the volumetric leakage current. The IR surface current is called the surface leakage current. So your insulators get real dirty. What it's going to do is it's going to change the capacitance of the insulator, and it's also going to change your surface current. It's not going to change your leak. It's not going to change your volumetric current, but it's going to change your surface. You see this happen every once in a while with spark plugs. When spark plugs get really dirty, if you ever reach down and touch the spark plug wire and you shock it. So this is just showing you. So the total current insulator is the vectored sum. We use Pythagorean theorem. You'll learn this in AC. This is not really important in this class. So the light flow. And I know it's almost time to go now. Electromagnetic waves at the extreme high frequency. So light frequency runs from about what? Oh, 1 times 10 to the 14th hertz, light over 1 times 10 to the 15th hertz. These are considered light. Of that, we have what we call the visible light spectrum, which runs from about 4.29 or 4.3 times 10 to the 14th up to 7.5 times 10 to the 14th hertz. In comparison, the FM radio band runs from 88 to, that's not 88 to times 10 to the 10 megahertz. The AM band is actually in kilohertz. The FM band is in megahertz. So this is the electromagnetic waves. So we have radio, we have microwave, we have infrared, we have visible, we have ultraviolet, we have X-rays, and gamma rays. You will start getting into radar and all of those high frequency. But this visible is just a very, very small part, and this ranges between infrared and ultraviolet. Now we use a lot of infrared, we use very little ultraviolet. Because ultraviolet is at a frequency that's very dangerous to us. Ultraviolet, the radiation of ultraviolet burns. Kills bacteria too. So we can use it. Some places where they go into those clean rooms, they literally put on special goggles and they'll walk into an ultraviolet to be, yeah, to be decontaminated. So this is just basically that. Now, what we need to understand, and we'll just look at this just a little bit, is that if I'm sending a wave through a conductor, we have a frequency. But it's just like waves coming in off the ocean. They have a link between the waves. So what we're saying is that we have a link between these waves moving into the conductor. So it's not a positive and a negative at the same time. So we could literally, if we had a wave, we could measure the distance between the peaks, right? Understand? Now we refer to that as what we call a wavelength. Well, actually, we can measure it anywhere on. It's just easier to see up on the peaks. Just like we have the distance between the waves coming in on the ocean, we have a distance between the waves being transmitted through a conductor, whether it's a light wave or whether it's a electromagnetic. Well, all of them's electromagnetic. So when we get into light frequencies are so high. So we're talking the terahertz that normally when we start talking about light, we don't use frequency, we use wavelengths. So this is the wavelength right here. So red would be around 600, 700 nanometers. Micrometers. Most of your light that I see is given in nanometers. For some reason, this thing that I got off the internet gives it in decimal micrometers. So, around 800, 600. So we use a lot of 600, 610 nanometers in fiber optics. We don't use a lot of visible light, and we don't use a lot of ultraviolet, which would be anything above, still say above, but anything that's got a wavelength of less than 400 nanometers. And then, of course, so what we're going to see, we use a lot of 1310, I think, which would actually be down below infrared. So we use a lot of those like electromagnetic waves in fiber optics. The one that we're going to use is, I think it's 810 nanometers, which would be up in the red band. And what's nice about this is that's 810 is right in here. So what does that mean? It means we can see this. So it's going to be red. So this is used a lot in fiber optics. 810, 1350. 1350 we can't see because that's back here past the infrared band. We use that a lot too in really, really high frequency applications. Standard fiber is up around 18. Are we okay? When we get into light, we're not going to talk about frequency. What they talk about is wavelength. And you can see the way the light. So right in here, green would be somewhere between 600 nanometers, 500 nanometers. Radio, anything in the radio and the RF band, we usually deal with hertz. The light, we usually deal with wavelength. Are we okay? So this is where we're at, guys. In fact, what we'll probably do, we're going to probably this is just an introduction. What we're going to do next class is we might stop what we're doing. One of the first things we're going to do is we're going to let y'all play around with a micrometer. Have you ever used a micrometer? This is outside mic, huh? A caliper is usually a pinch thing. A micrometer is usually it's either inside mics or outside mics. We'll see, and you'll notice when we get in there. And what we're going to do is we're going to actually take a bunch of wires and we're going to measure their diameter, and then we're going to transfer that and figure out what gauge that is, just to get you a feel of the different gauges and let y'all get used to precision measuring equipment. I think that box over there has a caliper inside there. A caliper, and it has a dial mic, which we use to measure thicknesses and stuff like that. An outside mic, which is what we've got, has got two jaws on it, and one of them's adjustable and one of them's not. It's stationary. And what we do is we have a dial that we turn until it touches. And the ones we got, by the way, are not digital. Y'all need to. There's a lot of people out there now that don't know how to read a clock.
Yeah.
I mean, they don't know how to read a regular analog clock. They have no idea what the hands mean because they live in a digital environment. So most of your mics, they do have digital mics, micrometers, but these are not. These are actually manual. So you learn how to read the dial and figure out how to do that. And we'll make sure we do that lab next class. Get y'all out of lecture into a little bit of lab. Then after that, we're going to start terminating some copper wire. We'll look at methods of terminating the wire. So we're going to deal with soldering. We're going to show you how to splice and terminate using solder, which is in my opinion, the best way. If you do it right, it's the best way to splice or terminate electrical conduction. And then we'll let y'all do that. And then we got crimp splices, and then a combination of crimp and solder splices that we'll look at. We're going to show you how to wire a wall plug up. We're going to show you how to wire Ethernet connectors up, wired Ethernet, how to do that. Huh?
Orange, white, orange, green, white, blue, blue, white, green, brown,
Orange, white, orange, white, orange, green, white, blue, white, green. That's the B. That's the B. The A, you swap the greens and oranges. All right, guys, y'all okay?